All right. Hi, everyone. Thanks for coming to the actually August edition, even though it's September, of the Distributed Systems Reading Group. We were delayed a week. Apologies. I got double booked and I couldn't find anybody to fill in time. So, and actually on that note, I will be passing the hosting baton as my travel schedule gets a little bit bananas here to Brian and Philip. Who one or both of them tend to come to these. So starting in, I guess, 3 weeks for that. So anyhow, for this month, we looked at the, or I guess we are looking at the FLP impossibility paper. We had a bunch of new people join, and talking to them, there's 2 requests. One was, it's the middle of summer, a lot of us are on vacation. Can we please do something a little bit lighter? Secondly, a lot of people weren't around for the 100 impossibility proofs, which I believe was the first or second paper that we did. And so a request for doing a classic paper rather than something from like, the last year or two. So this ticked both of those boxes. Hence this being the one. So the FLP impossibility paper is probably, it's often cited as being the most important fundamental result in distributed systems. It's a little bit like the halting problem, but in a distributed context. Before I end up giving like a full summary of this, I'd like to turn over to the group. Does anybody have a summary of this paper?
I can give give a try to give it a summary.
Awesome, thank you.
Okay. So this is Eleanor giving a summary, just to name myself. The paper that we read for the month is Impossibility of Distributed Consensus with One Faulty Process. The fundamental result that they demonstrate is that if you come up with a protocol for a distributed consensus on a fully asynchronous system with other assumptions about how this is operating, then it's impossible to avoid certain types of failure states. The first section, this is broken into 5 sections. The first section, they just introduced the problem, explaining that this is something that comes up, for example, with transaction commit problems, or when you're working with a distributed database and you need to decide if a decision, or rather if a change should be made or should be rolled back. But for this paper, they show that even for just coming to a binary decision, then you still have no possibility of ruling out this type of failure. They also explain in this introduction that it's important that this is asynchronous, that if you add synchronicity, if you add timeouts, for example, or if you start adding assumptions on speed, on processing, then this problem no longer applies. So it really sets a baseline for what type of problem they're working at, what type of system they're working at, and in particular, how broadly this applies. They also make very specific assumptions about messaging that come up. The second section is discussing what they mean by consensus protocol for this problem. So they start setting all of the technical bits about what exactly a processor is, what exactly they mean by consensus, all of which become necessary for how they actually demonstrate the proof, but are pretty detailed. The primary part is just that once a decision has been made for a process, it can't flip its decision. So all decisions are essentially final, because that comes up in how they discuss a lot of this. They sorry. From there, they get to the main results, which is that no consensus protocol is totally correct in spite of one fault. They spend a lot of time building up what exactly that phrase means. I translated it myself to that every consensus protocol, which is which is defined as they discussed above with the messaging protocol, must have a situation where a decision value will never occur, multiple decision values are reached, or just never reach a decision. So fundamentally, you cannot define a protocol that will avoid this. And then they just build it out from a sequence of lemmas. They show specifically that while this is impossible, that if you do start adding any assumptions that, like, for example, no protocol dies during execution, then you can start establishing results about how these things will behave and their ability to reach decisions. And they wrap up in a conclusion saying that this rules out solving consensus problems in one way, but by refining the model, we're able to do so in other ways.
Amazing. That was a fantastic summary. Thank you. Yeah, and just to dovetail on that last bit, it rules out consensus in the general case, the most general case. So when it is totally asynchronous and when it hits all of these very weak assumptions, even with something like, say, TCP, it still applies there, but we by adding stronger assumptions about the system, we can then say, well, under these conditions, it will succeed, right? And if any of those conditions fail, then we're back into the consensus has failed, right? So it just makes us really clear about which parts are required in a particular consensus algorithm. And I actually really like the hopeful last paragraph. That's like, yes, it's impossible in general, but this gives us a initial starting point to talk more directly about what's possible and what isn't in different and design protocols that are really clear about their assumptions, which I think is why this is, I might have the stat wrong, but I believe this is the most cited paper in the distributed systems literature, right? So it's like, it just shows up absolutely everywhere. So just to get the conversation rolling here with various folks. So we've looked at a bunch of different protocols recently. We've looked at Raft. We've looked at things like CRDTs. I just mentioned TCP, right? Does anyone want to take a stab at how these relate to, and actually, before I go into that, FLP is just the name of the three authors. So there's no deeper meaning there. It's just literally their first initials and last name. Does anybody want to go into the how any of those would relate to FLP impossibility and how they try to solve the problem? Let's maybe start with Raft, for example.
Yeah. Well, obviously Raft has timers, so it's not asynchronous in that very narrow definition of asynchronous. Thinking about CRDT now.
Yeah, so in Raft, it's both the timers and that it operates in rounds, right? So it's like, we can't just send a message and say, like, whenever you get this, execute, right? It's like, it's going to be on this round, that round, right?
It also seems like part of Raft's lack of timer asynchrony is specifically, it's kind of assumed that the timers are operating on a similar timescale. And I would imagine Raft does not do well if one of your timers is like 1,000 times slower than all the others, because like that node's going to get excluded, or it's going to slow everything down, or something terrible will happen. Whereas the FLP paper is like, the messages can arrive however they want, whenever they want. It can take like any number of finite message receive attempts to receive a message, which can be a big number.
One difference is that in FLP paper, they make an assumption that the process, if it fails, there's no way to know that it has failed. We cannot communicate to other processes. Whereas in Raft, we make an assumption in the protocol that the failures, the nodes, the processes that have failed, we can determine those failures.
Yeah, so in Raft, it's not that even that we detect failure, it's just that we detect timeout. So it might not have failed, it might just be the message is delayed, right? And so it's like, and that's the assumption in the asynchronous protocol. Somebody has their mic on and it's quite loud. I'm trying to find.
I think maybe you, Jenna.
Yeah, just muted.
Yeah. So that's part of what makes the system asynchronous in FLP is that we can't tell whether a process has failed or not, and we make no assumption. It's like it either faulted or it's just taken its time.
Yeah. So this question in the chat for CRDTs isn't the linking of causality in messages bounds the time and avoids the asynchronous problem. Does anybody want to dig into this one?
I'm not sure time is at stake in CRDT. I may be totally wrong, but my intuition when you said, disclosure, didn't read the paper. I read next month's paper by mistake. But my intuition is there's this notion of consensus. Like you make a choice and the choice is irreversible and you have to agree with the other one. And I'm not sure that's quite the same as I've received or I have not received this event. It's not a consensus. It's received or not received. It's not, of course, you have to have received the same event as the other one, but there's no picking a state in quite the same fashion, but I'm trying to understand how exactly that applies. But that's my intuition, that it's not timing, but the consensus part.
Anyone else? Right. So in CRDTs, or I guess even taking one step back, in the paper, they talk about this very particular setup, but that has less to do with the problem that they're trying to solve and versus their simplified model. It's just a simplification of like this broader class of thing, right? So being like, even in this really, really simple world, we still have this problem. With CRDTs, the assumption always is, and we've been playing with this a bit at Fission and like breaking this assumption to great effect, I think, that at some point in the future, like maybe it's millions of years from now, you'll all have agreed on the same state, assuming that you've all received the same messages, right? So in the way that they're phrasing the problem in the FLP paper is at a certain point in time, I should know that we're all in the same state. We've achieved some sort of an atomic right. And CRDTs specifically throw out atomicity and say, we will eventually receive the same states, but we make no guarantee about when. And so that's the weakening for those.
And no guarantee that we'll know when the other
and no
has
guarantee
reached.
that we'll know when. Yeah, exactly. Yeah.
That's
So a way that we've been playing around with this a bit is there's always this assumption, at least at the theory level, that you will eventually end up in the same state. Right? We always talk about it converging. Something we've been playing with is constantly always diverging, but still maintaining the nice semi-lattice properties, and saying like, we don't expect to ever catch up. In fact, we don't want to catch up. And we can even take like different paths through this structure by saying like, what if I hadn't seen these events and dropping them, right? And things like that. And so that's actually been a very fruitful area of exploration for us, which is yet another weakening of the system, right?
With CRDTs, then, is it still consensus?
It's not a consensus protocol, no. Yeah, but even so, FLP talks about the impossibility of consensus with one faulty process, right? But it still says really deep things about even the CRDT case, right? About you'll never be able to guarantee that a message was delivered, because that is knowing that a message was delivered is a kind of consensus, right? I'd have to send it and then receive it back, and we've now both changed our state to know this one thing happened, right? But you'll never, it's impossible to do that except under stronger assumptions.
Does it make a difference that FLP paper states that some processes reach a decision state, not all non-faulty processes?
Could you expand on that?
So the similarity with CRDT for consensus. So does it make a difference that not only some of the processes reach a consensus, not all non-faulty processes?
So the way that they phrase it in the paper is like, it's so weak that all of the well-behaved nodes should reach consensus, and then they go and they just do it with two. In something like a CRDT, it's fault-tolerant CRDTs.
Sorry to interrupt you. I think they state that some processes have to agree, non-faulty processes. It's not all non-faulty processes. So they are making a distinction there in that respect.
Yeah, you're right. Actually, I think that they say just even one has to be able to know that it's in the correct state. Yeah, which is very general, which is great.
Yeah, that strong assumption that it was, or just one, at most one faulty process and only one decision, just makes it so sort of extreme.
Yeah, their method of proof is really beautiful, I think, in this paper. That's just like so simple and like so like I think easy to follow, because it's such a simple setup. Is really nice.
Yeah, I really enjoyed the proof as well. It builds out very nicely. I would not mind going into it more, but that probably would take more time than we want.
Their proof technique is cited as one of the impacts that the paper had. That folks kind of like latched onto that proof technique and used it in other areas, and then also did proofs by reduction using the result from this paper. For folks who are interested, this is I'll put in the chat a link to. This was the announcement of the when this paper won the Dijkstra Award. And there's some great, commentary by some of the folks from the Principles of Distributed Computing community on sort of the lasting impact the paper had, which the paper was published in 1985, and this award was, it received this award in 2001. So, a good stretch of years where it had been around.
Yeah, and a non-Lamport paper that ends up being super well recognized, which is nice, because he's the big name. Though, I mean, frankly, Nancy Lynch has done so much work in the space, and probably should be better known, at least I think. So many of the papers and citations in papers that we've looked at, like if you just Command F and look up Lynch on basically any paper we've looked at, she shows up somewhere, which is amazing. So. Question in the chat: what's the relationship between TCP and consensus?
Well, that's you have to figure out if you've delivered a packet, if you need to resend it, right? At the very least, there's a the generals problem there, where like at some point you just have to pick a number of like sin and ack, and any more is like, well, that's good enough.
So could you say that TCP is a form of requires a form of consensus about message delivery?
It seems like it wants like it uses a weak consensus, because you're still not 100% guaranteed that everyone is on the same page, but you're relatively guaranteed. At least as far as I understand TCP. I have not like done a deep dive into TCP, so there's probably some stuff I'm missing there.
So I think you hit the nail on the head. That was one of my prompt questions that I had written down sort of in the notes. Just because you mentioned the generals problem, would you like to expand on that a little bit as well?
So I do not know it well. I've just like had it explained to me in conversations, and I think they mentioned it in this paper even. But it's the idea is you've got like two generals on opposite sides of a city they're sieging or whatever, and they want to coordinate so that they're attacking at the same time. So the general on the east sends a messenger over to the general on the west, and then like the general on the west needs to make sure that the general on the east knows that they received the message, so that they both attack at the same time, and like not have one of them attack while the other one thinks that that's not going to happen. And so basically, as far as I'm aware, it is not possible for both generals to be 100% certain, assuming they're like just running messengers back and forth, that the other general knows the correct time to attack. And yeah, I think that's the general's problem I'm familiar with, but I think there are other variants that are more decidable.
Yeah, so I think it's a nice summary of the generals problem. The famous variant is the Byzantine generals, where any of them might be faulty, and they may be in a power struggle as well as delayed, right? But it's this coordination problem, which is a particular phrasing of a distributed consensus, basically. So like it's a nice picture for like, well, how would this work in the real world when we're not just sending stuff over, copper wire and fiber?
In TCP, doesn't consensus protocol has to satisfy three properties: agreement, validity, and termination. In TCP, doesn't it doesn't satisfy the validity property. In that you only have one state, that all should have the same packets. It should also have, it's like all protocol agree on 0 value or 1 value, all these. So would we classify that as a consensus in that respect?
Yeah, so I think TCP is exactly, sorry, I should open this up to the rest of the room first. Anyone?
Assuming I've understood the question correctly, I think part of the thing with TCP is that like for each individual TCP exchange, it is basically binary. It's like have we exchanged the message or not? But then like that happens for all of the individual packets in or sessions or whatever. Like I said, I'm not super familiar with TCP internals, but like every single exchange needs to be confirmed in the same way, and so you end up with a bunch of confirmations like that. And ideally, if your TCP session has gone according to plan, at the end of it, you have like both agreed that you've received and sent all of the messages, I think.
Yeah, so it's exactly the case from the paper where we have two possible states: message sent, or message was delivered successfully or not, right? And there may be several rounds in TCP. So you want the whole message in this session, but for each round, you need to know, yep, I got it. And so that's when you look at TCP, it's like, people like to joke about this. It's like, prepared to receive a message. I'm prepared to receive a message. Okay, I'm sending the message now. Okay, sending the message. How long is the message going to be? And it goes back and forth like this. And if any one of those is missed, it's assumed that the message isn't delivered. But there's absolutely a case where the message was delivered, but not responded to, or that response was delayed or dropped or something. And so the message will be resent accidentally. And so we run immediately into FLP impossibility with TCP in really simple protocol with two possible states, message delivered or not. And I guess also the third possible state, message was delivered corrupted and is responded with, yeah, I got the message, right? So we have to always say under what conditions do we agree that the message was delivered. And in TCP, the case may be sometimes that there's a small edge case that we very rarely see that we got the wrong thing.
Because you have timeouts in TCP, can we consider it synchronous?
So we can consider it a synchronous protocol, yeah. So it will eventually stop and say that it didn't complete, but so we're really, in all of these cases, we're trying to build a synchronous protocol out of an asynchronous protocol, right?
Yeah.
And so there's still the case where there's a timeout, but the message was delivered. Right, and then we're going to try again after the timeout, right? So it's pretty reliable in practice, which is sort of the end part of the paper.
I got really puzzled when I heard the description by the assumption that once you've reached a decision, you cannot back out of it. And how crucial is that assumption? And is it easier to achieve a good protocol without that assumption? And I've been thinking in TCP, we certainly change status from not delivered to delivered, and so there's a change of status. Now, of course, the not delivered is also the initial unknown state, but let's say delivered or lost, but it can go from lost to delivered. Of course, it's delivered in the next round, so maybe that's a different variable gaining the status. But still, how crucial is that assumption? Forget TCP up to a point. Could breaking that assumption get us out of that result?
So I didn't follow the proof super closely, but it seemed sort of important to the way that they did everything, that like once a process had decided on the output state, the consensus state, whatever, that it couldn't go back because it was doing stuff with like commuting the states and finding focusing on places where the whole process of executing the protocol and figuring out what the consensus was moved from a bivalent state where like it was possible to go, depending on whatever the messages were sent, from like the undecided state to the 1 and the 0 state. And like the whole point of the proof is that you can force it to always remain undecided by picking the right or the wrong path, assuming I understood correctly. Like I said, I didn't follow it super closely. And so it seems kind of important that the processes can't change their mind.
Yeah, I could be wrong on this one too. I think that what they're trying to do is just keep it really simple, right? So if it could switch to another state, so if it's gone to 1 and now it's gone back to 0, you're now like, it's really hard to check that that you've ever hit consensus, because once you've made this decision, you could switch, right? So they're trying to show, like, even in the simplest possible, there's two processes, they have two possible states, right? If there's only one
change their
state,
mind, so you don't have to you don't have to track the fact that they changed their mind. Yeah, and I guess it's easy enough to reduce the change your mind case to the don't change your mind case by speaking about rounds. I had this state at round X, and then I had this state at round X plus 1, and then it might reduce to the previous case.
Or you might be able to build the change your minds protocol on top of the once decision protocol, maybe? I'm not entirely sure about that.
Yeah, which is what I'm saying. If you can do that, it shows the possibility extends to
Yeah.
the change your mind case.
Yeah, exactly. I was mostly thinking like the CRDT stuff did a similar thing where they showed how you can convert from op to state and state to op. And
Right.
so anything that applies to the one applies to the other. And so
Yep.
it seems like you could probably do something similar here, maybe, possibly.
Maybe. Okay,
Yeah,
thank you all for entertaining my interrogation.
Awesome. Yeah, no, it's great. It's great. Yeah, I guess the other bit that they talk about in the paper too, just briefly, right, is having better clock synchronization, right? Means that you could then more easily build asynchronous protocol. And you know, as you two were talking, I was like, well, you know, you're always going to have like it's not discrete; it's a continuous time in which, you know, messages are going back and forth, and they're not necessarily broken into rounds. But I guess we could just say that, you know, like at the limit or like at the Planck time, right? There's like some smallest possible round in which these are going back and forth, and you could, I guess, slice it up and think about it like that. In practice, I'm not sure how that would actually work out, because we're like, you would sending a message would be going through so many different rounds. Like, you know, I sent this on round 1 and here it is at round 3 billion. But interesting thought experiment. In a previous session, we had the author of the raft paper show up, which was pretty great to be able to pick his brain. And he was talking a lot about clock synchronization and how, like, yes, it's true that, you know, from a pure physics point of view, you can never like fully synchronize 2 clocks because of relativity. But maybe you can get them good enough that it doesn't matter for your protocol. Like, oh, it's actually kind of interesting.
Yeah, it definitely seems like if you can provide like bounds on the degree of synchronization, like calculus style, as long as you're within, as long as you can get close enough, you're good. It seems like a useful sort of assumption to be making if you're trying to prove things about protocols with timeouts or whatever.
I suspect a bit like calculus also, there's probably a kind of ratchet thing you can do. Like if you know you're within this bound, you can close the bound a bit. And then you know you're within this bound and you can close the bound a bit. And I'm sure there's a limit to that, but that's pure intuition. No, I don't know if that.
Is the limit to that
ages.
the limit?
Oh.
What?
Is the limit to that the limit?
It's been ages since I heard about it. I think I like attended a talk years ago, someone describing how NTP worked, and it had a similar vibe. It was like, by doing these shenanigans, and they were relatively cursed, if I recall correctly. It was a lot of shenanigan. We can like synchronize our clocks close enough and like improve the synchronization over time. So that is, as far as I'm aware, a thing. And NTP is one of the avenues you can look into if you're interested in that for some reason. And good luck to you.
Yeah, so I mean, clock synchronization is exactly a consensus problem. What were the I know very little about NTP other than it causes me headaches sometimes. What were the shenanigans that they went through?
So I barely remember, but it was like this was a like I watched a talk years ago, but I think it was something along the lines of by like timing how long it took for each message to get to the person you're synchronizing with, and then doing some very clever math, you could work out more than you would initially think about the full round trip duration, and like slowly
And
adjusts.
it gives you bounds on how much. how far
Yeah,
you are.
exactly. And then over
Mhm.
time, I think it like slowly came into synchronization. But again, this was years ago. Do not cite me as an authority on this to any degree.
Yeah,
So
like
the
So,
TCP server can be off as well. So they can also be not synchronized. So there are like other challenges as well. So there are multiple TCP server. You pick. Then there is agreement on, there is consensus there as well, like which value you would consider.
oh, like among the different sources of truth, basically, like which one of
Yes.
these clocks should I follow? Yeah, totally. And I guess for that, it can only really give you a lower bound on the distance, because on the internet we don't have control over the network topology, right? Like your message could get routed 3 times around the planet before it hits its its final destination, right? So it's certainly not going to give you an upper bound on distance. This is part of apparently Google synchronizing time with Spanner between its data centers involves custom hardware, i.e., laying cable between data centers, which is, I mean, pretty extreme, but it really simplifies the system.
So I did look quickly at the algorithm on Wikipedia, and they do mention the clock frequency is then adjusted to reduce the offset gradually, creating a feedback loop. So there is this ratchet effect.
yeah, and I just wanted to mention that ratchet effect is built using statistics. So the fact that it all works is mostly because statistics works out in the end when everything has, the expected values. So it's just based on the assumptions that, the distribution of different timings is going to be something that we can systematically prune to determine the true value.
And there's a very cute note about and the assumption that the travel time is symmetric between the 2 clocks synchronizing, which, oh, interesting. How reliable is that?
Yeah, I guess actually one way that applies to the problem that we've been discussing is that this uses statistics specifically to make decisions when it's trying to build that consensus. So it's not just agreeing on things the same way. It has a slightly different model, it feels like.
Totally. Yeah, it's agreeing on again. It's this same notion. It's not about consent. It's not full consensus, because full consensus is not only having the same value, but knowing that you have the same value. And we said CRDT, it's consensus without awareness of consensus. And in a way here, it's consensus with statistical awareness of consensus. We know that we're within a certain statistical distance of one another, but it's limited awareness of consensus. It's very interesting how the awareness of consensus is built into the definition of consensus. And relaxing that actually makes a lot of things possible.
Yeah, it's also interesting, this like refinement idea as well. Obviously, this has been used in NTP and I assume other places. A few of us, and I know a few folks from this call as well, have been exploring propagators more deeply recently, which is like a very general model of computation from Sussman and others over at MIT from the 70s that's being brought back more recently. And one of the examples that they like to give is refining a result over time. And so, estimating, the example that they tend to give is like estimating the height of a building by using, a couple tools, and over time getting better and better measures and then narrowing that down. And I wonder if there's like interesting consensus mechanisms to be built out of more of these refinements, as opposed to saying this is the value, just saying like over multiple rounds, we'll get clearer on what it is.
Well, next month's paper is actually a great example of that, which I did read, as I said. It's people have 2 sets and they're trying to achieve having the same set, but the set difference is being whittled down. It's exactly what's happening.
Yeah, next month's paper for those who are now maybe curious is a really interesting technique for set synchronization without prior context. So not knowing what the other side has, and just seeing like how close can we get, and then it can fail, but in successive rounds, you can start to pull out more information and start to build up a picture of the other side. Which is, yeah, actually, that's interesting. That's, I think, exactly what this is.
Yes, same. But you're right. I'm really curious in terms of, I'm interested in ID alignment and the notion for if you have a kind of Bayesian view of the world as what is likely to happen, and how much of that is done through back and forth in, well, I had that experience, and this changes the evidence and up to a point the priors, and you're kind of aligning priors by aligning record of experience. So it's something we all do by exchanging stories to understand the world. It's a very generic case.
Yeah, that's actually interesting. It sounded almost like you were going into like, and I know you have background with this truth maintenance system stuff.
Mm-hmm. Yep.
Is there much overlap between, well, actually, I guess truth maintenance and consensus? There's obviously some overlap. Just to riff, how much work is there done in like a distributed truth maintenance and reaching consensus, or is it more specifically just about the determining what's agreed and what isn't?
I'm not aware of distributed truth maintenance. Doesn't mean it doesn't exist. It's certainly what I'm trying to build, actually. So yes, it's of huge interest to me. I think a lot of it is solved by the in theory by the set reconciliation. But I say in theory because that assumes, and that's the assumption I'm trying to relax, that assumes that you have similar names for things. And how do you align the sets when you don't know that you have the way to name the set elements? That becomes a much more difficult problem. But I was thinking of the much more limited problem of, we have the same names, we align otherwise the claims we're making, or the events, the notion of what are the events, and the causal links between the events are supposed to be the same. But what are the weights on this, and aligning the weighting on the Bayesian network through exchanging events and facts, and what are the events that are the most likely to make you shift your assumptions. I mean, this is the how do you change opinions problem, right? What story will make you change your mind about something? And it is about not necessarily Bayesian, but it is evidence, an epistemic network, and finding what are the important stories that may make you reconsider evidence for a generic belief. That's what I'm trying to understand. But yeah, I think the notion that we're aligning views of the world from partial information, on the other hand, is universal, and that's been done, right? But because we treat it with set alignment and things like that, again, there's so many simplifying assumptions there. When we have to, is this the same type of story? Is this the same idea? What are we even trying to agree on? That is where it gets interesting to me. So this is almost more philosophy than computer science question, but it is related, of course.
Awesome. So we're getting relatively close to time here. So we have about, let's call it 10 minutes left before we do the wrap up. Does anybody have like burning thoughts or questions about the paper to sort of take us through the end of this. Also totally fine if not, but if so, this is the time. Okay, awesome. Does Byzantine have a formal definition in distributed systems? It does. So there's a paper entirely on this, the Byzantine generals problem, from Lamport, I believe. And it says you can be in one of three states. You can be offline, so you can be down. You can be buggy, or you can be acting normally. I can't remember the specific phrase for non-faulty, but it has a specific word. And so it's, and the definition of being buggy or faulty is just that you're not following the protocol directly, like literally, like whatever the protocol is, you're not following it. So it could be either malicious or just doing the wrong thing. There was a bug in the program. You know, your spinning platter was hit with a cosmic ray. It doesn't really matter. It's just you're not following, at least in that round, you didn't follow the protocol. And then different protocols will determine if you can become non-Byzantine again. But yeah, it has a formal definition.
I have a question from the paper. The lemma 3, where they mention case 1 and case 2. In case 2, there is a row which is deciding run that they use to prove like figure 3 in that. So why row is I understand that row is an admissible run, but why is it a deciding run?
If anybody has this more hot loaded in their brain, please.
It's lemma 3 case 2.
Sorry, what was the question again?
So in case 2, in lemma 3, there is a so if you look at row, they define a deciding run from C0 to A.
Mm-hmm.
So why is it a deciding run?
My understanding, let me actually look at that again.
Is it sigma instead of rho? Just, I don't see a rho in there.
I see P and P prime, and I see sigmas. Yeah.
Yeah, sigmas. Yeah, sigmas. So from the connecting from C0 to A, the dotted line in the diagram, figure 3.
Right. I remember this part of the lemmas building why you must always have another bivalent configuration that you can find later, where events are applicable. And what this part is arguing is just that if P prime, so this is the part that relies on the fact that the processes can be faulty. And essentially, I understood this, that if you do eliminate a process by just saying it no longer takes an infinite number of steps, then you can create a situation where you reach a contradiction about how the outcomes of the runs are going to occur, which isn't a very specific answer, but that's the extent to which I remember it right now.
Yeah, and you're asking for, because they define some really specific properties. It's like it's an admissible run, it's a deciding run. You're asking why this is a deciding run. Is that specifically deciding run?
Yeah, because they mention when the case 2 starts, they say that it's a schedule. So why is it a deciding run? Because that's the underlying assumption that they are proving wrong.
It looks like it's a deciding run by lemma 1, because they say by lemma 1, sigma is applicable to D and it leads to an I-valent configuration, which I think means that because it leads to a specific valent configuration, it's a deciding run by the definition they provide, where a deciding run or a run is a deciding run provided that some process reaches a decision state in that run. So if it reaches an I-valent configuration, then some process has reached a decision state. And so I think that's how that works. But like I said, I did not follow the proof super closely. So if someone else has a better answer.
Yeah, they don't say why it's a deciding run. They just say consider any deciding run in which the particular process is just not taking any steps. So they don't state that it must exist. They essentially just state it does exist and go from there. And I imagine it's arguable that such a thing does exist, but they don't really they don't expand on it in the case 2. They just ask, or they just say consider one, and if you have one, then the conclusion that you reach is that things are going to be contradictory. Yeah.
Thank you for explaining.
So another question from the chat, just to as we're heading into the home stretch here. The last section really discussed consensus when the number of dead processes is known. I just moved. It sounds really similar to Raft. I'm curious about the sense if asynchronous communication can be used to set up something like Raft. So I think this is similar to the discussion with TCP, but if anyone would like to take this one.
I'm a bit puzzled by, can you use asynchronous communication to set up something like Raft? I think Raft is built on an assumption of asynchronous communication and then adds synchronicity precisely by adding timers. But the underlying protocol, I would say, is asynchronous communication. Now, again, I did not read the paper, so I'm not sure how related it is to this last section. Somebody else should take that. But the second part of the question, I think, is clear, yes.
Yeah, so in any protocol, you have to bootstrap up from some asynchronous messaging and then start adding stuff on top of it, right? And say like, now we're going to add a counter, now we're going to add all these other things. So Raft does bootstrap up from asynchronous messaging, but then adds like stronger assumptions to it by giving you timeouts, by doing the heartbeat, by doing all these things. And so it tries to get you into a synchronous situation, and it will fail in an asynchronous one, like in a truly asynchronous one, which is also a part of this paper that says like, we just have to be really clear about our assumptions, right? Like in Raft, if none of them respond back, you don't have a protocol at all anymore. Like you're in a partition, you know, by definition now, right? So it's like it becomes really clear what you're working with, and you would not be able to build Raft out of like without that consensus. Without that synchronicity requirement and doing that heartbeat and all those things. That's actually, people get really excited about the leader election, but it's really the heartbeat and the timeouts that make Raft even possible. But that's building it out of these asynchronous components.
Tangential to that question, I don't really have a specific question, but I am really interested in the specific way they built up the system for messaging. That it's just a very general message system that acts non-deterministically with pretty limited conditions, and I'm kind of curious to the extent to which other message systems have to be built out of this one, or if it's the case that we're able to avoid building a message system that behaves this way.
Just to clarify, you mean with this idea of some sort of a shared buffer that they use? It's like you're writing in and then people are reading out and stealing messages from the queue?
Yes. The way that all these systems are talking together plays a very important role in why this result is impossible. And I'm curious to which that particular part can be avoided.
It seems sort of like inherent to physics, I think. Like it felt to me at least like it was kind of a model of like just how like communication over a network, where I guess communication in general is inherently unreliable, where like the message could be delayed. And in fact, it's a nicer model even than physical reality, because messages don't get dropped or duplicated by anything other than the processes themselves. But like it still seems like the message might take a long time to get to you. Like that whole thing seemed sort of just, that's how it is, unfortunately. And
Yeah. Go on, sorry.
the multi-set buffer thing seemed mostly like an implementation detail, and I didn't see it being critical to the proof. But I also, like I've said a few times now, I didn't follow the proof super closely, so I might have missed something there.
I think that it partially models the asynchrony, because a process could go to the message buffer to ask for a message, and even if there's one there for them, they might still get a null message. And so they could continue to infinitely like get null messages, and at some point like get the one for them. And I think that the messages, actually, this is one part that I wasn't totally clear about. The messages are directed at one process, right? Or they're addressed to one process, I should say.
So there is follow-up assumption as well. So once a process reads a message, it does some computation and sends follow-up messages, which is an atomic operation. And when it sends its message, it atomic broadcasts using atomic broadcast. So all non-faulty processes receive that message.
Okay.
This is also inbuilt. This is the assumption that they are also making with the system model that they defined. So how relevant these assumptions are like to the final proof, I'm also have questions around that.
No, it's a great question, and I mentioned Shannon's model in the chat. Like, I don't know if alternatives to Shannon's model of communication. I mean, or at least alternatives that fall outside the Shannon's model of communication. Now, there are a few extra assumptions in this model beyond the base Shannon model. And yeah, I'm not clear that alternatives to those extra assumptions, which would still fall within Shannon, would not be subject to the same thing or reducible to the same thing. But it seems to me there's not that much extra assumptions beyond. It's a way to express, the extra assumptions are a way to express, like the other things we saw, simplify our understanding, but I don't think it constrains within the Shannon-Weaver model that I can think of.
I think what they're trying to, because I also found that strange in the paper. I think what they're trying to do again is simplify and just be like, let's not even worry about this part of it. Even when this part works in this like really simple model, we still have this problem. What was my take on it? But yeah, it also sort of like raised a flag for me. So just a quick time check. We're actually now 1 minute over. So I'm going to hit the stop record button.